See you later.
Okay, so today we are covering our last section is 6.2. I only have, for those of you on the recording, you probably have a full set of notes, but for those of us in the classroom right now, you only have the notes through 6.2a. I will give you the notes as we go, but I have the homeworks all listed. So we learned about what if you had area between two curves and all the various ins and outs of that. And so what if we wanted to find the volume? And so, John, remember with calculus, we're talking about this kind of changing um, circumstances. If you constantly, with the area, we would, think of a series of rectangles, and you'd slice those rectangles into smaller and smaller and smaller pieces. And so there's, paper thin, even thinner than that. But the idea of you added up all of those little tiny rectangular areas, then you have the area of the whole thing. And the smaller you make your rectangles, the less you have pieces of it either hanging out or not really in the area of your curve. And so that's why we ended up making this, this delta x, which became a dx in our integral. That was the width of each of those rectangles, and that width got infinitely small eventually. Okay, that's the idea. So let's say that you wanted to know the volume of a loaf of bread. Okay, the volume of a loaf of bread. Well, depending on your loaf, if you have your plain whites, whatever, they might be actually pretty rectangular, but they have a little bit of a different shape, and sometimes they're a little taller in the middle and a little less tall on the outsides. Okay, you know what I'm talking about here. Okay, so it becomes this weird irregular shape. Okay, but what if you thought about each of those individual slices of bread? They are more or less, now, especially when you get towards the edges, you can often see the difference between kind of the front side slice and the back side slice. But more or less, you could think of those as about the same on both sides, or you can kind of split the difference, use kind of the midpoint, if you will. Okay, and so then you could find those individual volumes of each of those slices, add them all up, and ta-da, you've got the volume of the whole loaf. And now you've accounted for, when they were a little bit, shorter slices on the ends versus kind of maybe the more taller slices in the middle. But you'd have accounted for that because you did each of those individually. Does that make sense? Okay. So similarly, let's say I've got this thing here that I'm trying to find the volume of, and this is some weird shape here, and the so what if I split it up into, kind of like a loaf of bread, where I split it up into these pieces that have they all have the same width. Okay, and note, now at least I have a kind of a fighting chance. And notice that they kind of took out the curvature of it. They made them, be a little more squared off, if you will, right? And so it's not going to be perfect, but at least now we have kind of a fighting chance of kind of putting it into bite-sized pieces, if you will, of figuring out what each of those individual volumes are, and then we can then find the volume of the entire thing. Okay, by adding each of those up, we can then make it, say even smaller and smaller slices, and your book talks about this x sub I star, which is basically anything in between here, and we kind of have glossed over that, and we don't really need to worry too much about that. But imagine, eventually it gets to be these smaller and smaller slices, so the slices are infinitely small. You're eventually, while this is not going to be a very good well, I mean, it's going to be better than nothing, right? But it's not going to be a super accurate estimation, but it's going to be decent. The smaller we make those slices, as we get them infinitely small, we'll get down to essentially exactly what we need to have. Make sense? Conceptually, everyone okay? Gentlemen, I want to take a little trip back to geometry.
Oh, yikes.
In geometry, let's talk about the volume of a solid. Okay, the volume of a solid, specifically a right solid. So let's say that you had something like, well, let's say that you have, well, your traditional box. Okay, Okay, your traditional box, you have a width, a length, and a height. Okay, and so what's the volume of the box? Okay, so length times width times height, right? And so depending on where you got things are, so everyone okay? The length times width times height. Now, with that length times width times height, if you the area length times width times height. Think about the length times width. The length times width is itself a rectangle on the bottom, right? And it is essentially, and if you take the area of that base and multiply it by the height, you have the volume of the box, right? And so in geometry, we ended up saying that for any for any prism, it was the area of the base. They used a capital B to show area of the base times the height. And so this length times width was buried inside this. And why this was useful, because let's say then I had something like, let's say I had a trapezoid as my base, and I have this box, and so if I wanted to find the volume of this thing, doesn't it make sense by the same idea of what I had here? Think of all those slices essentially, that I could take the area of this base, the area of that trapezoid, because it's note that all those slices all the way through here are going to be a trapezoid. So I take the area of that trapezoid times the height, and ta-da, I've got the area of that trapezoidal prism, and I'm just using this formula. Is everyone okay with that?
I thought we were finding volume.
You're right. It was supposed to say volume. Good catch. I screwed up. Okay, I had one thing in my brain and wrote the other thing. Okay, so volume is length times width times height. This will confuse people in my recording. And then, but volume then for is the area of the base times the height. Okay. Good. Now let's. Back to. And also, John, what's the volume of a cylinder?
That's a good question. 1/3. So we have to get back
Cylinder, not a pyramid.
Half them. That's
plus or no.
Well, here's the deal.
Pi squared.
It's this thing, right?
Yes.
There's our cylinder. Can't you use the same idea? Isn't it the area of the base times the height? And so the volume of a cylinder is going to be, what's the area of the base? Pi r squared times height. There's your volume. Does that make sense? Okay. So with all of that, gentlemen, the volume of a prism or a cylinder is the area of the base times the height. And with a cylinder, you can then specifically say pi r squared times the height. Your book will call anything that has curves in it and part of its base as a cylinder. So even if it was, if you had something that was, I don't know, looked like a half circle and then made a base, they would call that a cylinder. Okay. One way or another, it's a right prism of some sort, and specifically, I guess since it's curved, they call it a cylinder. Okay. So everyone okay with that? So, gentlemen, it should not be a surprise to us that if we're dealing with the calculus of this, okay, basically we're going to ask for the individual slices all the way through here, right? And so how do you deal with that? You deal with it with calculus, and so and the width, that change of x being infinitely small, we eventually call that dx when we're dealing with our integral. So it turns out that what's going to happen here is that the volume is going to be a of x instead of f of x, right? A of x, the area of the slice at any given moment, times the width of that slice, and so that's the differential of x, right? So there's your a of x dx. It's not a times x times dx, it's a of x times dx. So far so good? Okay. this is no different than we were finding the area, and we said it was the integral of f of x dx. Okay, and the area was the under the curve of f to the x-axis. Okay, so the region bounded by y equals the square root of 4 minus x, the x-axis and the y-axis. Does that look okay to you? Okay. Is revolved around the x-axis. Can you imagine? Imagine that this is like a big vat of jello, and you're going to do this, and you're going to rotate it around the x-axis in such a way, so here's the x-axis, and you're going to rotate it around the x-axis, and so it's going to eventually scoop out that looks like. Can you imagine in your mind what that looks like?
Yeah. No.
Okay. Hopefully. So if this were to rotate around, okay, and partly we're doing 2 dimension or drawing on 2 dimensions when we're thinking about a 3-dimensional thing. Imagine that as this comes around, okay, and eventually kind of cuts out this cup-like looking thing, sideways cup, essentially. See how if you were to rotate that purpleness around, how you cut out kind of a sideways looking cup. Yep. Okay. Are we okay?
Yeah.
Anyone not? Okay. So, gentlemen, do you see that if you have a series of discs, right? There's all these discs, and the disc keeps getting smaller and smaller and smaller as you get towards the right, and it gets bigger and bigger as you get towards the left. That change, right? That changing size is going to be accounted for with that integral of a of x, and then the dx is the infinitely smaller and smaller disk that you're going to have that you would eventually add all up to find out the whole solid. Make sense? So note that we are now. It looks by inspection, it looks like this thing goes from 0 to 4. Okay. So let's see here. If we, and you can probably see that in the equation itself that makes sense here. When it hits the axis, what's the y value? 0. And so we could set this equation: 0 equals the square root of 4 minus x, and so you square both sides, so 0 equals 4 minus x, and then add x to both sides, so x equals 4. And so sure enough, yep, we think that where it hits the axis here is 4. Okay, so it confirms that we're going from 0 to 4. And the reason why we know it's 0 is because they told us that the y-axis is one of the boundaries. Okay, so we have this integral from 0 to 4. Okay, now here's where we then have to think a little bit about this. Okay, the radius would be from the x-axis up to here, right? And I didn't draw it evenly, but the radius should be the same on top and bottom, right? Okay, so the radius is the which value, the x value or the y value? It's going from here to here. Is that's a y length, right? And it changes depending on where you are, but you can tell how big it is at any given moment because this is the equation that tells you what the y is based on which x you're on, right? So remember, these discs they're a series of discs, a series of circles. What's the area of a circle? Pi r squared, right? And so it's pi r squared dx. Wait a second, Mr. Mulhern. You got r's and x's, but trust me for a moment. Okay. But remember, so it's pi times, let's see here. The radius is equal to the which value, did we say? The y value, which, by the way, y is equal to the square root of 4 minus x, right? So r is equal to square root of 4 minus x. So this is the square root of 4 minus x squared. Yes. Let me pause. You okay with this? What's a beautiful thing that happens for this particular problem right now? square root cancels with the square root cancels the square root, right? So we've got from 0 to 4 of, and gentlemen, pi is just a constant, correct?
Well, that one is.
And so we can pull it out, and then we've got 4 minus x. Well, Mr. Mulheron, the 4 is a constant too, but notice it's not a multiplier in there, right? Whereas pi was a multiplier of everything. Okay? Dx. Let me pause. Are we okay? Gentlemen, now this is no different than anything you've ever done before. I think you can take it from here. Just integrate from 0 to 4. Right? So the antiderivative, the whole bit, yep. Plug it in 4, plug it in 0, subtracting all of that. I will tell you right now, you should get about 25.13 in the end. And I don't want you to use your calculator really until the very end. It turns out to be about 8, or exactly 8 pi.
I got 8 pi.
Did you? Good. And what is that? Is that about 25 something?
Yeah.
So about 25.13. What I guess I don't think it told us where to round to. So 25.13. People agree with this?
Why wouldn't you want it as just 8 pi?
It depends on our purposes. Okay. If I was asking you about the how much water could this cup hold? Well, it'd be 25 cubic units. Let's say we're in centimeters or something, and 8 pi doesn't mean a lot to us, right? And so it kind of goes back and forth about what kind of an answer we want or care about. And so and I guess I will get back to you, but before you leave today, I'll check the answer keys to see which way they go with it. Okay.
Yeah.
Good. In the end, you should be easily able to go from one to the other, and just fine, right? Yes, sir. That's it. In the end. Okay. Not too bad. Okay. So really, I think the front end of this was just the two things are going to be this. One, what we just discussed in the front and making sure you understood the concept, and I think that's what took a while here. And then the second thing is, for some of you, this idea of rotating is going to be a little tougher, and it's going to get tougher in the future lessons because we're going to start rotating it about other axes instead of just the x and y axis. So we'll talk about that. Gentlemen, here is a region bounded by y equals 1/2 times 2 minus x to the third. Notice, can I distribute that 1/2? No, because it's to the third power. And so can I distribute the third power? No, it's not 2 cubed minus x cubed. It's 2 minus x times 2 minus x times 2. There's a whole lot of math that goes in there, so we're not going to bother with that, okay? And the y-axis is revolved, it's bounded by this, and the x-axis and the y-axis. So here's my curve, here's the x-axis, or the y-axis, here's my x-axis. So essentially, this is the region I care about. Okay, there's more, obviously, to this graph, but it's not bounded by the rest of it, so we don't care about that. There's the part we care about. Agreed? We are going to rotate this, revolve it around the y-axis. Okay, so if we revolve it around the y-axis, okay, can you, in your mind's eye, figure out what that looks like?
Yeah.
Okay. Hopefully, you have some sense of if I were to revolve it around, it's going to end up having this kind of a conical looking thing, but almost like a hat, right? It's not truly a cone. The cone goes as straight edges. This kind of has your curvy. Oops, what am I doing here? Has the curves to it, but nonetheless, you can see that there's going to be. You can here's your radius, right? It's helpful to put that radius in there, and then here's our series of discs, right? Okay, so we need to find the volume of the resulting solid. Gentlemen, first of all, what is our radius?
Our radius?
Is it X or Y?
Y.
Isn't the radius an X value?
Yes.
Everyone see it? If you don't, please let me help. Everyone see this? The radius is an X value? Okay, so the radius is an X value. So we remember when last time it was a Y value, we just got to plug in what Y is. Well, this one, we don't know what the X is, but we could work backwards, couldn't we? So this one is going to be done in terms of Y, so it's going to be a dy rather than a dx kind of thing. So let's do this. Let's solve for X. What's the first thing I'm going to do?
0y.
No. So if you, I see. So to find I think what you're suggesting is to zero out y because, well, actually, I don't know if that's actually particularly helpful. What we would probably do to find our levels of our limits of integration, note that's going to be from here to here. And so you would, what's the x value? The x value is 0. And so I plug in x for 0 to figure out where this is exactly. By inspection, it looks to me like it's 4. But we'll figure that out for sure in a second. For now, what I'm trying to do is just figure out what my radius is. And so my radius we decided was x, so let's get x by itself. So in this, how do I get x by itself? What's the first thing I do?
Multiply by 2.
Multiply by 2. 2y is equal to 2 minus x cubed. Now what?
Cube root.
Take the cubed root of both sides. So the cubed root of 2y equals the cubed root of this side, which means 2 minus x. Now what?
Would it be plus minus 2x?
What do you think?
Yeah.
It's not an even root. It's not a square root.
No.
So no, right? Because the cubed root of 8 is not plus or minus 2. It's only 2, right? Okay. And so now, gentlemen, you can either subtract 2 and multiply by -1, or you okay with me just adding x to this side and subtracting this to that side? So I eventually have x equals 2 minus the cubed root of 2y. Let me pause it, okay? Good. Now so this is equal to 2 minus the cubed root of 2y. Okay. Now, by inspection, we think it's 0 to 4. We could actually figure out, so at this spot, the x value is 0, correct? And so we could find f of 0, right? That's y. And so 1/2 times 2 minus 0 cubed. 2 minus 0 is 2. 2 cubed is 8. So we've got 1/2 of 8, which is 4. So sure enough, it is 0, 4. And so we agree with that, right? So, let's see here. We're integrating from 0 to 4. Remember, since our radius our x's, then our limits. It's going to be in terms of y, and so our limits are y values. Yes, sir.
1/2 times 4.
1/2 times 8.
8.
I knew it was going to be 4, and so then right. 2 cubed is yeah. Thank you. Good catch. Okay. So we're going from 0 to 4 of this area pi r squared dx, which excuse me, dy, because we're going this direction. And note, and I'm going to just be painfully slow about this. It's 0 to 4 of pi x squared because it's we know that r is equal to x, and still dy. And what is x? Well, from 0 to 4, remember, so we're going to have of pi times 2 minus the cube root of 2y dy. Let's pause. We're okay. Okay. So at this point, can we see that this is going to, that 2y is to the, oops, this is squared, right? Oops. Right, because that's x, so x squared. Can we see that this is going to get to be some fairly complicated antiderivative? Okay. This one we are going to use our calculator. Okay. So will you use your calculator? By the way, gentlemen, some of you have discovered, I've seen you working on some of these problems, you've discovered that you can use alpha y or alpha whatever you want, and that's fine. But quite honestly, your calculator doesn't care. It doesn't know what this variable is, and the variable is just a variable. It doesn't care. So if you do everything in terms of x, even though it's written down as y, it will be fine. Make sense? Yes. Where's your calculator? Last day, perfect.
I got stolen last week.
Mm-hmm.
Came back from formation, my locker was just wide open. It was gone.
What do you got?
5.026. Yeah, 5.026.
5.0265. Is that right?
Yes.
Okay. So as I'm doing this, I am realizing I probably need to give you some guidance about when to use Math 9 and when not. And I guess, if it is this overly complicated thing where you've got essentially a power inside of a power and all of that, it probably will be something you do by your calculator. At the same time, that being said, we had this guy, and that one was fairly straightforward. So I will try and give you a little bit more guidance about when to use Math 9 and when not, and I'll try to sort that out before we leave today. Okay, hey John. Exact same problem, except what changed? They asked us to revolve around the x-axis.
Won't the answer be the same?
No. Note that the radius is, you got really long radii here, right? Whereas before, the biggest radius was that long.
Yeah, but won't the answer be the same because they're same area?
No, it's 2 now.
But that rotation makes it different. If I had,
oh, it's a 3D shape. Never mind.
Think if I had this rectangle, if I rotate it around this axis like this, I get a certain shape. But if I rotate it around, say, where I rotate it, this way, I get something short and squat cylinder as opposed to, so it's a wider radius. I don't know. I'm not saying it right, but do you see it's different?
I thought I kind of forgot it.
Yeah, it's in 3 dimensions. You're right. But the area itself is the same at a given moment. But then but now you're taking different size discs as you're going through. Yeah. Okay. So, can you imagine? So again, here's the space we care about. Okay. And we're going about the x-axis, so here's the x-axis, right? So if you rotate that around, gentlemen, hopefully you can see what this looks like. It's going to end up looking something like this, where you have a series of, here is that biggest disc, right? You got a series of discs in here. Joan, what is your radius, x or y? Everyone agree that the radius is the y value? So the radius equals y, which, by the way, equals 1/2 times 2 minus x cubed. Let me pause. We okay? So, and we're going from, what's our integration from what to what?
0 to
0 to 2. So now we're going to be, since our radius is y, that will be written in terms of x, and so it will be a dx kind of thing. So our limits of integration will be the x values from 0 to 2. Everyone okay?
Yeah.
And remember, it's pi r squared dx, which is pi times y squared, right? Dx. And it's pi times, and what is the y? It is 2 minus x cubed. 1/2. Thank you.
Is that
1/2 2 minus x cubed. This whole thing squared. Yes, sir.
in the second one? Is that y?
Y. So it's r is y. So I just changed pi r squared to pi y squared. And what is y? 1/2 2 minus x cubed.
We can use math 9 for this, right?
In a moment. Okay. I would like to at least acknowledge, gentlemen, that you've got a product here that is being multiplied and then or taken a power of. So what's 1/2 squared? 1/4. And then what's 2 minus x to the third squared? 2 minus x to the sixth. So you've got 2 minus x to the sixth. Does everyone see that part of it?
Yeah.
And you've got 1/2 squared, which is 1/4. That's a constant. That's a multiplying constant, right? So you got pi and you got 1/4. So I'm going to pull pi over 4 out. And I acknowledge that Math 9 will take care of a bunch of this, but I want to also sharpen your other skills and seeing the further math that's in here as well. Now, since we've got something inside of this bigger power, it's going to be a little bit more to do with, and so I am okay, I think, with Math 9 at this point. And so, what do you get? That's not what they had.
Oh, yeah.
I had 14.3615. Is that not right?
Yeah, exactly. Yep, that's what I got.
Okay, so we're using Math 9 for this, right? Okay. Is everyone okay with this? Now, I haven't been consistent about where to round to, and again, we'll follow the directions in the book as we go, right? So far, so good.
Last one.
Okay. Questions? Last one. Let R be the region in the first quadrant bounded by the x and the y-axis. So here's the y-axis, here's the x-axis, and the horizontal line y equals 1, and the equation y equals the square root of x minus 1. And so that graph looks something like this, and it makes contact at y equals 1 down here, but we care about this region here. Question?
So wouldn't it just be 0 equals square root of x and then square root of x and then 0 just equal plus or minus?
Let me pause. 0. Okay, 0 to figure out where that. So if we set.
Well, because y equals 1 and then y equals square root.
So 0 equals square root of x minus 1. And so here's.
Why is it 0?
I thought you just told me to say that.
No, I said 1 equals square root of x minus 1. Because y equals 1 and then y also equals.
So y equals 0. So there's one reason why I might set y equal to 0, but then y eventually equals 1. So 1 equals the square root of x minus 1. Maybe we can compromise. Do you agree that maybe both of them seem relevant? Everyone okay with this? Now, some of you are seeing ahead on this, and you'll see what's going on in a moment here. But so around the y-axis, can we agree it looks something like this?
Yeah.
Okay, and looks something like this down here, and has this shape to it.
Why don't we just add a circle?
What's that?
Why don't we just add a circle?
It's not that we're adding a circle. And quite honestly, it goes down a little further than this because we're trying to. If we're rotating this shape around the axis, isn't it going to cut out this cup kind of idea?
Oh, it's like
right. This is like a blade that's going to cut through.
Yeah.
Yes. Yeah. Okay. And so actually, let me back up. I don't know if I actually even like this part of it. Okay. Gentlemen, are we going? What is my radius, x or y?
Y.
Isn't my radius going to be this?
Yeah, that's x.
Y.
Isn't that? But do you agree this is where the radius is?
Yeah.
And isn't that an x value? Right, side to side, left to right. That's going to be x value. So the radius is equal to x, which is equal to, well, I have to go figure that out, right? So y equals square root of x minus 1. What do I do to get x by itself? So y plus 1 equals square root of x. Now what?
You square both sides.
So y plus 1 squared equals x. Everyone okay with that? Good. Now, gentlemen, the limits of integration, because we're going to be, since the radius is x, then the whole thing is going to be in terms of y, right? So therefore, your limits of integration are x values or y values? Y values. John, this one we actually don't have to go solve for what those limits are. They actually tell us. What are those limits? 0 to 1, because they say the x-axis, so y equals 0, and they tell you y equals 1 is the upper limit here, right? So from 0 to 1 of pi r, which is x. So I'll skip a couple steps from what I had been doing. So here's my x, right, squared.
So it would be 4.
Thank you. So that whole thing squared, right? Here's my x. Okay with that? So as Mr. Jansen pointed out, by the way, you okay if I pull this pi out? And so it's y plus 1 to the 4th dy.
That's a math man, bro.
Okay. And in this particular case, and I guess I don't know how I feel about it. We quite honestly could have done it here as well. The fact that the complicated thing was that it was this negative x, but they actually showed the integration for it. This isn't too terrible. If you have your u be y plus 1, then what's du?
Du is u to the 4th, but then du must be 5.
So hang on. So if u equals y plus 1, then what's du?
Oh, dy.
dy.
Oh yeah.
Right? So if y equals 0, then that implies u equals what?
0.
1. And if y equals 1, I'm just changing my limits of integration, then that implies u equals 2. Yes?
Yeah.
So this is the same as from 1 to 2 of u to the 4th du.
It's easy there.
And this is relatively easy. So it's 1 to 2 of what?
U to the 5th divided by
5 over 4u.
No, actually, excuse me. We integrated, so this is no longer here, right? So we. Okay with that?
Holy.
Yeah.
And that's not terrible.
No, that's easy.
So pi times, let's see, here we have 2 to the 5th over 5 minus 1 to the 5th over 5. So pi times 2 to the 5th is what, 32? over 5 minus 1 over 5. So 31/5 times pi.
So we just wrote math 9 for this one.
I will on Schoology tell you which ones I want exact and which ones not. And so if it says exact, then that would imply maybe you're not using math 9, right? Makes sense? What is 31/5 times pi?
19.47.
19.477, you said?
Yeah.
Is that rounded correctly? 478?
478.
Okay. Gentlemen, if you were to math 9 it either at this level or at this level, does it give you that same answer?
Yes.
Did you do it? Okay, gentlemen, I don't think I changed this one on your sheet, but so 2 through 6 is due for next time. Seniors, thank you for, actually, let me shut this off first.
Goodbye.